So my presentation is visible to everyone? Yes, Madhusudan?
Yes, sir. It's visible.
Yeah, good. So today we have a last class and also fifth unit. So that is a last unit. Okay, and there is a sensorless control of PMSM drive. So I hope all of you know about the special electrical machines, that is a PMSM and BLDC motor, correct? So if you don't know, then little bit I will cover in the today's class. So what is a PMSM and BLDC motor? Because I think those who already took this subject of the Bharat sir, so he already covered this topic. There is a PMSM and BLDC, and those who are not uh, took this subject, that not this subject, that is a Bharat sir subject. So don't worry about that. So I will cover the brief introduction of the PMSM and BLDC motor, and then finally I will start the final topic, that is a sensorless operation of the PMSM drive. Yes. Yeah. So in the previous class, we discussed the space vector PWM, and the difference between the VSI and CSI, cube law between the speed and power, and development of the dynamic model for the electric drives, and finally simulation tool to check the performance of the electric drives. Okay. So today's lecture, in the today's class, we will discuss only one topic, and that is a major topic is a sensorless operation of the PMSM drive. So starting with introduction of the permanent magnet synchronous motor. So PMSM stand on permanent magnet synchronous motor. So there is a full form of the PMSM. So PMSM drive. So starting with the introduction, okay, and then just one minute, somebody want to join the class. Yes, sir. Check. Yes. After that, difference between the PMSM and the brushless DC motor. And second one, there is a BLDC motor. So nowadays in all electric vehicle, majority company use the BLDC motor. Okay. So BLDC stand on brushless DC motor. So brushless direct current motor. Okay. So nowadays in the electric vehicle, we have a three motor. One is an induction motor, PMSM, BLDC, and SRM. So SRM stand on switch reluctance motor. Okay, so SRM, there is a switch reluctance motor. Okay, so we can say this PMSM, BLDC, and SRM all are the special electrical machines. Correct. So nowadays, majority company use this induction motor, permanent magnet motor, and SRM motor for the electric vehicle application. After that, we will discuss the working principle of the PMSM drive, then speed control of the sensor and sensorless PMSM drive. So how we can control the speed of the PMSM drive. And finally, we will discuss the sensorless operation of the PMSM drive. And finally, I will discuss that my PhD work. So there is a simulation result of the sensorless PMSM drive. Okay. So there is a for your kind information. So how we can make the model in the MATLAB, and how we can do the analysis of the sensorless PMSM drives. Okay. Yeah. So starting with the introduction, so there is a PMSM drive. Okay. So we already know meaning of the drive, correct? So whenever we can say drive, then we have to control the speed, otherwise the torque of the electric motor. And for this unit, we have a PMSM. So there is a permanent magnet synchronous motor. Okay. So yes, we can say there is a input is a VDC, because we have to control the output voltage of the inverter, correct? So we can say input of the inverter, there is a DC voltage. So this is a VDC, and that VDC may be the from the battery side, otherwise maybe the we can connect the rectifier, and then we can convert into DC. Okay. So maybe the rectifier, otherwise the battery, but we need the constant DC link voltage, correct? So that is based on the selection of the power supply. And then we have a three-phase inverter. So we can say, yes, we have a 6 switch, and that is maybe the IGBT, maybe the MOSFET, yeah, maybe the thyristor. So based on the application. So we can say this is your inverter part. Okay, so this is your nothing but inverter part. Okay, we can say inverter, three-phase inverter. And output of three-phase inverter is nothing but your again AC supply. So output of the inverter is again AC supply. So you can see this is a three-phase R, Y, and B. Okay. So this three-phase, there is a PMSM. There is an input of the PMSM, and this is your PMSM motor. Okay. So this assume as a PMSM. There is a permanent magnet synchronous motor. Okay. And then we have to control this motor, correct? So we have to take the some feedback signal, correct? So this is your feedback signal, correct? So feedback is a rotor position sensor or sensorless operation. So we can say as a feedback, there is a maybe the sensor, otherwise the sensorless operation, correct? So we can operate this PMSM maybe with sensor, and that sensor, there is a Hall effect sensor. So we can say Hall effect sensor. So role of the Hall effect sensor to sense the position of the rotor, correct? Because on the rotor side there is a no winding. On the rotor side only the permanent magnet. But in the case of the stator, that is a stator is same like the induction motor, correct? But only difference between the PMSM and synchronous motor is a doubly feed motor, correct? In the case of the synchronous motor, there is a doubly feed motor. We have to give the AC supply to the stator and DC supply to the rotor in the case of the conventional synchronous motor. Okay. But in the case of the PMSM consists of the conventional three-phase winding in the stator and permanent magnet in the rotor. Okay. So stator structure is similar to the synchronous motor, correct? Otherwise, we can say induction motor. But whenever we can say rotor structure, so there are no winding on the rotor, but there is a permanent magnet in the case of the synchronous permanent magnet synchronous motor. So there are the major difference between the PMSM and synchronous motor. Okay. The purpose of the field winding in the conventional synchronous machine is done by the permanent magnet in the PMSM. Correct. So we can replace that rotor winding by the permanent magnet, and that is a major advantage. Sorry. The conventional synchronous machine required the AC and DC supply. Yes, suppose you want to operate the conventional synchronous motor, so we have to give the both supply. AC supply for the stator and DC supply for the rotor. Okay, so we have to give the both supply for the armature as well as the field. So that's why we can say conventional synchronous motor is a doubly feed synchronous motor, correct? Where PMSM requires only the AC supply for its operation, and that AC supply for only for the stator, because on the rotor side there is only permanent magnet, so no need to give the power supply to generate the flux, because permanent magnets so itself they have a flux, correct, and there is a strong flux density. So one of the greatest advantages of PMSM over the counterpart is the removal of the DC supply in the field excitation. So we can easily remove the field excitation. There is a DC supply from the PMSM, and there is a biggest advantage in the case of the PMSM. Okay. So yes, so we need the feedback. There is a sensor less, otherwise the sensor. Okay, and here this is a voltage, current, and here is a theta and the speed. Okay, so there is a feedback signal. So there is a speed, current, torque, and controller. Correct. So we have to give everything in the controller. Maybe the controller there is a microcontroller, maybe the FPGA, maybe the microcontroller, maybe the FPGA, any controller, correct? Any controller we can use. And one side there is a reference signal, and reference signal there is maybe the torque or speed, okay? And one is a DC link current, correct? Because we have to maintain the DC constant, correct? For the inverter input, correct? So this is a basic schematic layout of the your PMSM drive, and this is a common for the every drive, correct? It is not any special requirement here. That is a common. Only special requirement that is a rotor position. correct? So this is the rotor position. There is a special requirement because on the rotor side there is only permanent magnet, so we have to sense the rotor position where motor need to rotate. That is a 30-degree clockwise, yeah, 30-degree anti-clockwise. Based on the rotor position, we have to operate the this switches of the inverter. Correct? Yes. So in the case of the yes, any confusion in the previous slide? Any confusion in the previous slide? Okay. So in the synchronous motor, the rotor rotates at the speed of the stator revolving field. So working principle is it is the same like the conventional synchronous motor. So we know synchronous motor is always rotated at the synchronous speed. So we can say 120 F by P, correct? But induction motor we can say it is not operate the synchronous speed, correct? And there are the sleep concept of the sleep. But in the case of the synchronous motor, we can say it is always operate at a synchronous speed, correct? So same like the PMSM, it is always operate the synchronous speed because it is a basically a synchronous motor. But advancement, it is a we can replace that DC excitation by the permanent magnet only, correct? The speed of the revolving stator field is called the synchronous speed. Okay, that is a simple concept. If you know about the fundamental concept of synchronous motor, then you very well know about the speed formula as well as the working principle of the synchronous motor. Correct? The synchronous speed, that is omega s, can be found by the frequency of the stator input supply. Yes, that is a supply frequency. Okay. And the number of pole pair, there is a small p. Okay. So small p indicate there is a pole pairs, correct? And capital P indicate the poles. Okay. So yes, student, in the case of the formula, suppose you want to calculate the speed. So that capital P, that is a number of poles, but small p, that is a number of pole pairs. Okay, so we know n equal to 120 F by P, and F, that is nothing but your supply frequency. Okay, so we can say F is otherwise simple F. Okay, that is a supply frequency. P is a number of pole. Okay, suppose that is a small p. Suppose small p, then we can say P equal to capital P divided by 2. Okay, so we can say n is a synchronous speed, f is a frequency of the AC supply, that is in hertz, and p is a number of poles. But that is a small p. Suppose in the small p, then we can say small p is a number of pole pairs, and that is a by p by 2. Okay, and this is a general formula for the synchronous motor even. So this is a not new for the PMSM. So same formula we have to use for the PMSM drive. Okay, so speed we can calculate n equal to 120 F by P. Okay, and P where there is a number of poles. Okay, yes. Now classification of the permanent magnet motor. Okay, so here I written the permanent magnet. So PM stand on permanent magnet. So PMS permanent magnet we can divide into two category. Okay, so there is a PM we can divide in two category. One is a BLDC and another one is a PMSM. Okay, so one is a brushless DC motor and second one is a permanent magnet synchronous motor. Okay, so we can say classification. So direction of the field flux. So first classification based on the direction of the field flux. So which direction flux will generate. So there is a two classification. One is a radial field and another one is a radial axial field. Okay, so based on the direction of the field flux, we can classify the permanent magnet motor in the two category. One is a radial field and second one is a axial field. So what is the meaning of radial and axial? So radial field means a flux direction is along the radius of the machine. Suppose your direction of the flood, whatever generate the flux, that direction is suppose along the radius of the machine. Then we can say it is a radial field. And whatever the axial field, the direction of the flux there is a parallel to the rotor shaft. Okay. So axial flux, there is a direction of the your flux there is a parallel to the rotor shaft. Okay. Yes, just one minute. Somebody want to join the class. Yes, Narayan. Yeah. So yes, second type, that is axial flux. So direction is the parallel, flux direction is a parallel to the rotor shaft. Then we can say it is a axial field. So finally, we can say based on the direction of the field flux, we can classify the two category. First one, that is a radial field, and second one, that is a axial field. Okay. Second classification, okay, so there is a shape of the induced EMF. So we can say classification A, classification B, and classification C. Okay, so second classification, there is a induced EMF. EMF, that is a electromotive force, correct? So that is a BLDC motor, tapezoidal back EMF. So in the case of the BLDC motor, it will create the tapezoidal back EMF. Why tapezoidal back EMF? That we will discuss in the next slide. Okay. And another, that is a PMSM, that is a sinusoidal back EMF. And why sinusoidal? So that we will discuss in the next slide. Okay. So based on the induced EMF, we can classify in the two category, that is a BLDC and PMSM. Third
Sin
class,
sir,
yes,
sin sir, sir that IM machine means IM means what sir?
I am.
What bullet? Yes sir.
In which slide? This slide, yeah.
This
Here.
slide
This one, correct.
third bullet.
I am, that is an induction machine. I am stand on the induction machine.
Induction machine has a variable reluctance.
So this is a special type of induction motor. So do you know that as a synchronous reluctance machine? Do you heard about that motor? That synchronous
Sir, but
reluctance machine and switch reluctance.
induction motor rotor is cylindrical. No sir. How is that variable reluctance can
Yeah,
be?
so in the case of the induction machine, and that is a variable reluctance, so what we have to do for the variable reluctance, we have a rotor, correct? So we have a two type of synchronous motor, that induction motor, wound rotor, and one is a squirrel cage rotor, correct?
Yes sir. Yes
So
sir.
for the for the design of the variable reluctance, what we have to do for the design of the rotor, so we can vary the reluctance. So we can design the rotor, so we can easily vary the reluctance. So spatially we design the structure of the rotor, so we can easily vary the reluctance. And that reluctance, based on that variable reluctance, we can control the speed of the motor.
Since sir,
So
sir, I think that
structure,
IM stand for inset magnet. Inset magnet machine, sir. You can see that right side flow chart at the bottom is written.
mhm,
It is not a
mhm.
induction motor. One is surface mounted
Just
magnet,
one minute.
another is inset magnet.
Yeah, there is a classification. There is a surface mounted permanent magnet, and another one is a internal mounted permanent magnet. There is a classification of the type of the induction, that PMSM. There is a type of the
Yes, sir.
PMSM classification.
IM stands for that thing, sir. I think not a induction motor, sir.
Hmm, I will verify this thing. I am. I will verify that thing. Okay. I will verify that thing. The IM machine has the variable returns because one motor is there. That induction motor, we can design that squirrel cage rotor and wound rotor, so we can easily vary the reluctance, and then based on that reluctance, we can control the speed of your motor. But still, I will verify this IM. So IM, that is like inset magnet. Yeah, what? Correct. So I will verify that thing and let you know. Okay.
Okay, sir. Okay.
Yeah. Yes. So shape of the induced EMF, there is a yes, there is a, we can say, two type of classification: BLDC, brushless DC motor, and that is a tapezoidal back EMF, and PMSM, that is a sinusoidal back EMF. Okay. And mounting of the permanent magnet. So based on the mounting of the permanent magnet, we have a two classification. That is a surface mounted permanent magnet. Okay. So without the silency, so we can just a surface mounted and internal mounted permanent magnet. So this is a IM. So hopefully this IM, it is the same like internal mounted, but still I have to verify this IM. Okay. But as per this slide, so I can say internal mounted permanent magnet, that is a IM. Okay. But still I will verify this thing and let you know. Okay. So yes, in the IM, so for this slide, as of now, we can say there is an internal mounted permanent magnet. Okay, instead of this induction motor, so I can say that is a internal mounted. Okay, for the internal mounted machine has a variable reluctance which vary the rotor angle. Okay, so based on that reluctance, we can vary the theta, correct? And based on the theta, we can control the speed. But in the case of the surface mounted, SM stand on the surface mounted machine has a quite is a fixed reluctance for any rotor angle. Okay. Therefore, this lead to the uniform air gap. Because of the field flux, there is a fixed reluctance. So we can say uniform air gap, resulting in the equal magnetization inductance for the direct and the quadrature axis. Okay. So we can say LD and LQ, LD and LQ parameter. So LD and LQ is nothing but your quadrature axis inductor and direct axis inductor. Okay. Yes. So we can say yes. Classification, there is a three category. One is the direct direction of the field flux. Second one is the shape of the induced EMF, and third one is the how you can mount the permanent magnet on the rotor. Okay. So every classification have a two sub classification. Okay. Yes. So I was talking there is a back EMF. Based on the back EMF, we can classify the motor, correct? So you can see the figure number 1, there is a BLDC motor, and we can mount the stator in the such a way there is a concentrated stator winding. So in the case of the BLDC motor, shape of the stator winding there is a concentrated. Okay. But in the case of the stator, in the case of the PMSM, the shape of the stator winding that is a distributed. Okay. So distributed in the induction motor. So this is the same like induction motor. Induction motor. But this is a concentrated winding. Okay. So there is a concentrated winding. So because of the concentrated winding, it will create the tapezoidal back EMF. So because of the concentrated winding, it will create your tapezoidal back EMF. Okay. So this is a time, and this is your back EMF voltage. So we can say EB, because of your concentrated stator winding. But in the case of the distributed winding, it will create your sinusoidal back EMF. T, and this is your maybe EB. Okay, so this is for the PMSM, and this is for your BLDC motor. Okay, so that's why we can say PMSM and BLDC both are the permanent magnet motor. So that's why here I written classification of the permanent magnet motors, because structure wise and everything is controlling and everything is same. Only difference is your stator winding. Otherwise, on the both machine, we can say on the rotor side the permanent magnet controlling is same, everything is same. But only difference is that is your concentrated winding and distributed winding. Correct? Yeah. So you can see the structure of the sinusoidal as well as the distributed winding. So figure A, that is your distributed winding. Okay. And figure B, that is your concentrated winding. Okay. So you can see the pictorial view. So this is your PMSM motor. It is a similar like your induction motor. And this is your concentrated winding. So we can say it is a concentrate at one location. Correct. So and we can make the three phase. There is a phase A, phase B, and phase C. So this is your BLDC motor. This is your BLDC, and this is your PMSM. Correct? Yeah. So just for your knowledge, so difference between the PMSM and the BLDC motor. So just 1 minute. Yeah. So yes. So we can say difference between the PMSM and BLDC. So PMSM there is a feed with the AC, and BLDC there is a feed with the DC. What happened? Yeah. Okay. And sinusoidal back EMF, there is a back EMF is sinusoidal, but in the case of the back EMF, there is a tapezoidal, otherwise you can say the square flux density. Okay. Back EMF, there is a sinusoidal, there is a drive by the winding and magnetic design. And back EMF, there is a tapezoidal, there is a driving by the winding and the magnetic design. Okay. Yes, back EMF is a sinusoidal, then current is also sinusoidal. But in the case of the BLDC motor, current is a tapezoidal because back EMF is a tapezoidal. For equal resistive loss, power density is less. But in the case of BLDC motor, for equal resistive loss, power density is 15.4% higher than the PMSM because of the concentrated winding. Okay. The conduction and the switching losses are higher because of the three-phase transistor inverter conduction mode. But in the case of the BLDC, because we can say there is only two transistors operate at a time, in the BLDC case, we have to operate only two leg at a time. So we can say there is a 120-degree mode, 120-degree or 180-degree conduction mode. So this is not a part of this subject, and this is a part of that special electrical drives. So there is a Barasar subject. But suppose somebody want to do the research for the electric vehicle, so they might be know about this thing, correct? And that is important for the research. Yes, torque ripple due to the commutation is the current is low. So in the case of the PMSM, torque ripple is low, but in the case of the BLDC motor, torque ripple is high because of the that is a concentrated winding. The coil of the distributed winding are not coaxial, and they are rather than the distribution in the various slot. Yes, because of the sinusoid distributed winding, so all the pole pitch is covered, correct, for the one phase. But in the case of the coil, the concentrated winding are the coaxial. This means all the winding is the same magnetic acids, correct? And what about the back EMF equation? So there is a back EMF equation. There is a similar like the induction motor. There is a 4.44 N phase frequency into flux, correct? But in the case of the BLDC motor, 4.44 N phase frequency flux, but one more component, there is a Kp and Kd. There is a pitch factor. Kp stand on the pitch factor. Okay. Yes, this is a pitch factor, and Kd stand on the distribution factor. Okay. So there is an additional component in the case of the BLDC motor. And torque equation, in the case of the PMSM motor, there is a 3 by 2 P by 2, 3 by 2 P by 2, and P is a number of pole, lambda F minus LD minus LQ into ID into IQ. And similarly for the BLDC motor, EA into IA plus EB into IB plus EC into IC divided by omega M. That's a torque. Okay, so torque is nothing but your power upon omega, correct? So this is your difference. Okay, so this is a simple difference between the
Yes, sir.
PMSM and
Yes,
BLDC
sir.
drive. Yes, Ashish. Yes.
Sir, that third last point, please explain once again.
Third last point. Yes. Coil distribution.
Yes, sir. Yes, sir. Can you show in that in figure how that is happening?
Yes. Yes. Just 1 minute. The coil distributed winding are not coaxial, correct? They are rather than the distributed in various slot along the air gap periphery. This one, this point.
Yes, sir. Yes, sir.
Yeah. So in the case of the BLDC motor, the coil of the concentrated are the winding coaxial, and this means all the winding is the same magnetic field. Yes. Yeah, so you can see this one, this figure, slide number 8, figure number 1A. Correct? So we have a three phase. We can say we have a three phase. Correct? So this is R, this is a Y, and this is a B. In the case of the PMSM, that stator winding, that is a distributed winding, correct? So you can see this is a phase A. So maybe we can say this is a pole slot 1, slot 2, slot 3, up to maybe slot number 15, correct? So this is a slot 1, slot 2, slot 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So total slot is a 13, correct? So 13 slot, and we have a three phase winding, correct? R, Y, and B, correct? So slot equal to 13, and we have a three phase supply. So we have to divide this 13 slot into equally three phase, correct? So we can say this is a R phase. We can say this is R phase. This is a Y phase. And this one, there is a B phase. So you can say, you can starting one phase for the Y winding. For the Y phase, your first turn is here. So maybe this is a slot is 1, 2, 3, 4. This fourth slot, correct? And starting point is here and ending point you can see. Ending point is here. So this is a one coil, correct? I can just change this color of this. Yeah. So you can see starting point is here. This is starting point for the Y phase, and this cover the entire the slot. So slot number 1, 2, 3, 4, 5, 6, 7, and 8. So for the one coil, for the one phase is cover the total 8 slot, correct? For the second turns, again that is cover the 8 slot. So you can see for the design the one phase, how many slot they are covering? They are covering the many slot, correct? So here this line, it is written the coil, yes, the coil of the distributed winding are not in the coaxial. It is not in the coaxial. They are, second statement, they are rather the distributed in the various slot along the air gap periphery. Yes. So from this figure, you can say it is a not coaxial. It is a not concentrated to the one slot. It is a distributed to many slot. It is a cover the many slot to make the one complete the coil. Correct. But in the case of the BLDC motor, this is a BLDC diagram, BLDC motor diagram. Okay. And suppose you can see this is a slot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 13 same slot. And we have a phase, three phase. So this is a concentrated winding, correct? So you can see phase 1, this phase only, slot number 1 and slot number 2. Only 3 slot is covered, and we can take the one phase only. So starting point, this is a starting point and this is ending point. So we can say current is going here and current is coming here. So within a 2 to 3 slot, we can make the one phase. Similarly for the phase 2 and similarly for the phase C. Correct? So we are not covering the many slot. Then we can say it is a coaxial. So this point, yes. The coil is connected in the concentrated winding are the coaxial. It means all the winding has the same magnetic axis. So you can see all the winding on the same magnetic axis because we can cover only the less number of the slot, correct? But in the case of the PMSM, we can cover the many slot for the one coil, even one phase. Now got it?
Yes, sir. Okay, sir. Thank you.
Yeah. Yes. So this difference is not important for this subject, but this difference is important for the parallel subject. Okay, those who took the parallel subject. So this is the most important part. So there is a difference between the PMSM and BLC motor. Yes. So there's an advantage and disadvantage of the PMSM drive. Yes, every application is not 100% correct. So few advantages are there and few disadvantages are there. So first we can see the advantages. The DC field winding of the rotor is replaced by the permanent magnet. So there is a major advantages. We can replace the DC field winding by the permanent magnet. So we can get the more flux density. The advantages of elimination reduce the field copper losses. Yes, we can remove the rotor winding. So obviously there is a copper losses is reduced, correct? So there is a zero copper losses. Lower inertia, rotor inertia. Yes, so we can say no copper winding. So we can say yes, moment of inertia is less, correct? Higher power density, yes, because of the permanent magnet. So compared to the copper winding flux density, permanent magnet flux density is a very high. Okay, that's why we replace the field excitation with the permanent magnet. More robust construction of the rotor, correct? Because no copper winding, simple, you have to take the permanent magnet, maybe the neon any permanent magnet, real earth permanent magnet, NDFEB permanent magnet, any type of permanent magnet you can take, and you can make simple shape that is a cylindrical, and then we can say now our rotor is ready. But in the case of the simple synchronous motor, we have to take one iron bar, yeah, any aluminum bar, any material, and then we have to make the winding on the rotor, correct? So that we can say more robust and consistent of the rotor. So these are the important advantages of the PMSM. But what are the disadvantages? Yes, loss of the flexibility of the field flux control. How we can lose of the flexibility of the field flux control? Because motor is continue rotating, so it will create the temperature, correct? It will generate the temperature. So because of the temperature, there is a demagnetization effect. So that's the second point you can see. Possibility of the demagnetization effect. Because continue motor is running, so it will create the temperature, and that effect of that temperature on the permanent magnet. So permanent magnet is losing the flux, correct? So that will ultimately, after some time, it will reduce the flux density. So we can say yes, there are the major disadvantage in the case of the PMSM, other as BLDC motor. There is a demagnetization effect. Application, use of PMSM, there is a high efficiency, not induction motor. So high, because of the high efficiency, we can say everywhere we can use the PMSM, otherwise BLDC motor. Better controllability, we can control the very easily. Sensorless operation also possible, that we will discuss. High torque to weight ratio, yes, because on the rotor side there is a permanent magnet, so that's why it's a high torque to weight ratio. High energy density, low acoustic noise compared to the DC motor and the induction motor. No excitation losses, because we need no need to give the DC excitation, only we have to give the AC supply to the stator. And fast dynamic performance. So these are the many advantages. So based on these advantages, we can use them in various applications, correct? But nowadays people use this motor in the electric vehicle. Yes. Now, just overview of the speed control of BLDC motor with the censored base. Okay, with the sensor base. So sensor base means we have to use the encoder. Okay, maybe the encoder, maybe the proximate sensor, or we can say Hall effect sensor. Hall effect sensor. Otherwise, we can say the encoder, correct? So role of this, all the sensor, maybe the encoder, maybe the proximate sensor, maybe the Hall effect sensor. Role of the all the sensor to sense the rotor position. Okay, because on the rotor side there is a no winding, only permanent magnet. So we have to sense the rotor position, and then we have to operate our inverter switch, correct? Yes. So first we have to sense the rotor position. So this signal is coming and we have to use the sensor. Here is a sensor. Okay. And based on the sensor, we can sense the rotor position, and that rotor position we can give the feedback, correct? because once we have a theta, then we can easily calculate the speed, correct? So ultimately there is a speed and it is a feedback. So we have a reference speed, so this is a reference speed, and we have a actual speed, so we can compare, and this is a speed controller, and speed controller maybe the PI controller, maybe the PID controller, maybe the fuzzy logic controller. We already discussed this thing in the first semester also. And then we have a PWM inverter, okay, and then finally we have to give the three-phase controllable power supply to PMSM. So this way we can control the speed of the PMSM drive, correct? But this is a sensor based, correct? We have to use the sensor. To present the sensor have the several disadvantage. So why we have to go with the sensorless operation, correct? So reduce the reliability because of the sensor. There is a reduce the reliability, increase the cost because maybe the sensor cost, maybe the one proximity sensor cost, maybe the 1000 Nepali rupees, correct? So ultimately it is a increase the cost. Increase the weight. Suppose one sensor weight is maybe the 1 kilogram, yeah, maybe the 500 gram, correct? So ultimately it will create the weight. Size, yes, you need to implement the sensor, so it will increase the size of the overall system. Yes, you have to give the power supply for this sensor, maybe the 9 volt, maybe the 5 volt. So increase the complexity of the drive system. So because of these 5 disadvantages, we have to go with the sensorless operation. So we have to remove this component. We have to remove the sensors. And this sensor is not a voltage and current sensor. This sensor is your position sensor, correct? So we have to make the position. We have to find out the position. So based on that position, we
Excuse me,
can.
sir.
Yes.
Excuse me, sir. Sir, that resolver means what sort of sensor, sir? Last encoder is resolver.
Encoder, correct? Encoder,
Yes, sir.
proximity
Last
sensor.
yes, sir.
So
One
we
potentiometer, other LVD.
yes, yes.
Fourth one resolver.
Yeah, this one now. Yes.
Yes, sir.
So what we have, yeah. So for yes, one, yes, I will cover that part. So we have 4 main devices. There are the measure the position, correct? So one is a potentiometer, okay. Second one is a linear variable differential transformer that we can use to measure the position. Optical encoder and resolver sensor. So resolver sensor is what? So we have a disk. We have a disk and there is something like that. So this one is maybe the black color. So we can say this is a black color and this is a white color. So this is a white and this is a black. This is a black. This is a white. This is a black. This is a white. This is a black. This is a white. Black and white. So B stand on black color. Black color and W stand on white color. So resolver is nothing but this type of one disk. Okay, there is a round disk. Okay, so there are the 2 slot. One is a black slot and another one is a red, white slot, and another one is a black slot. Correct. So one LED is there. So one LED light is there. So what is the use of this LED light? So LED light is continuous sensing the signal. So which color is there? Black color or white color? Based on this color, LED feed the signal to the controller. Correct? And based on this number of slot, how many white slot are there and how many black slot are there? And then we can dictate the rotor position. Correct? Suppose your number of pole is a 4-pole motor, correct? And number of pole, there is a 4 pole, and this slot is maybe the this white and black slot. This slot maybe the 40. correct? So based on this 40 slot, we can say 40 divided by 4. So we can say 10. So every 10 rotation, we can complete the one circulation path. And that we can sense by the LED light. So this is nothing but your resolver
Yes, sir,
sensor.
but the LED will emit light. How it
Yes,
will
that is
sense
a
light,
emit
sir?
light. So with the LED, there is sensor is there, so that will directly give to our data to the controller. LED is only light
Yes,
emitting diode. It is only feed the only light.
LED output of LED is light and input is voltage. But
Mhm.
how color is sensed by LED, sir?
So one more sensor is there. So there is only collect the data. In with this LED, one more sensor is there plus sensor. So that sensor part is only collect the data. So how many number of black slot is there and how many number of white slot is there. So this sensor is nothing but that counter. So that counter, that counter just read the count. How many counts are there? That
Okay, sir,
counters
what
is
is that
there with the
type of sensor which can sense the color, sir? Name of that sensor that can sense the color.
So that is many sensors are there. I forgot the name. So that is a sensor is simple. Just they are sensing the which type of colors are there. So black color is there. Yeah, white color is there. Yeah, pink colors are there. So based on the color, they just count the number, and that counting of the number we can use the counter. But currently, I forgot the sensor. So which type of sensor we can use for the color for the color observation.
Okay, sir. Okay, thank you.
Okay, so basically this is your resolver part. Okay, so resolver is a simple disk, and there is a black and white color combination, and one we have a LED. There is a light. There is a just light is feed, and based on that light feeding, so their counter is count the number of slot. How many slots are there? 10, 20, 40, and then based on the slot, we can find out the rotation. Okay. So basically, these are the four type of sensors we use for the rotor position. Okay, and maximum we can use optical encoder and the resolver because this sensor is a small size. Okay, so yes, most commonly we use the encoder and resolver. Here I written most commonly we use the encoder and resolver sensor for the find out the rotor position of the PMSM drive. So this is a simple structure of the your sensor based operation, correct? And we already know these are the disadvantage of the your sensor based operation. Yes. So this is the simple structure of the sensorless operation. So speed control of PMSM drive with the sensorless operation. Same diagram, everything is same, but you can see here there is a no sensor. Sensor part is not there. So without sensor, how we can say where we have to rotate the motor, maybe the 30-degree clockwise, yeah, maybe the anti-clockwise direction, correct? So based on the voltage and the current signal, so we have to measure the voltage and current of the power supply, correct? So based on the voltage and current signal, we can estimate the rotor position. Okay, based on the voltage and current signal, we can estimate the rotor position. So you can see speed and torque estimation. So speed and torque estimation we can estimate by the voltage and current signal, correct? And speed we know, once we have a speed, then we can also calculate the speed, correct? So we need only one quantity, maybe the speed, yeah, maybe the theta. And then is other components are same for the sensor base, correct? So advantage is more compact device. Yes, advantage is more compact device because we remove the sensor. Low EMI because absent of the connecting lead. Whatever component you add in the circuit, then EMI will generate, correct? Electromagnetic interface. Low cost position encoded device is avoid. yes, we can avoid the low cost position encoding device to sense the rotor position. We can easily take the we can easily take the rotor position by estimate the voltage and current, correct? So by using the voltage and current signal, we can estimate the rotor position. Increase the mechanical robustness, yes, because of the absence of the sensor, we can increase. Suitable for the hostile environment, including the temperature. 6.1, ensure that inertia of the system not increase. Correct? Suppose you design any control algorithm and you can implement the voltage and current signal, and suppose you are going with a sensorless operation, then we have to consider also, so your system weight is not increase. Correct? And low maintenance required. Yes, obvious low maintenance, because we no need, we don't have a additional sensor to sense the rotor position. Okay. Yes, this is, you can remove 1314. The rotor position of electric machine by measuring only their voltage and current sensing. Okay. The method are used designed to sensorless, encoderless, or self-sensing. So we can say sensorless, otherwise encoderless, because there is no any encoder resolver. So we can say the encoderless, otherwise the self-sensing. PMSM, the rotor position can be determined by the back electromotive force or by the position dependence of the inductance, flux linkage, and sensing. So any parameter we can use where rotor position is dependent. Okay, maybe we can say the inductance. Yes, inductance is depend on the rotor position. We can say the voltage and current parameter. We can say the flux. So any quantity that is depend on the rotor position, so that parameter we can take and we can estimate the rotor position. Okay. So simple
So, sir,
concept. Suppose you
sir,
want to estimate the speed. Yes. Yes. Any confusion?
sir, yes, sir, that voltage or current, at least we are sensing voltage and current. We are measuring voltage and current, and to
Yes.
measure
Yes.
that we need maybe per current we need Hall sensor. To measure voltage we need voltage measuring instrument. So how we can say this is sensorless? We are sensing
So
some parameters.
yes. So for the sensor base, so you can see the previously this sensor base, we have to also the measure the voltage and current, correct? For the sensor base operation, we have to measure voltage and current. Additionally, we have to put the encoder, maybe the encoder resolver, yeah, maybe the any sensor to sense the rotor position. So in the sensor base operation, we need required the voltage sensor, current sensor, as well as the rotor position sensor. So whenever you add the rotor position, so it will add the additional circuit. Okay, and we have to give the additional power supply for the sensor. Correct. But we are now saying there is a sensorless. So sensorless means it is a not like only that is a voltage and current sensor. Sensorless means we are saying there is a rotor positionless. It is not like we are not using any sensor, any type of sensor. Yes, we have to use the voltage and current sensor. It is compulsory to operate your device. Without the voltage and current sensor, we cannot able to control our drive. It must be used the voltage and current sensor. Here, meaning of the sensorless means we have to remove the position sensor. That means there is a sensorless operation. Okay, not
Okay,
like
sir,
voltage and current.
and that removing sensor only possible in PMSM only, or in other motor also like BLDC.
Yeah, other
Can you
motor
remove sensor?
also. In the BLEC motor, in the case of the SRM motor. So everywhere we can remove the that encoder and Hall effect sensor. That is possible.
Okay, sir. Okay.
Yeah, so many researchers are doing the research on the sensorless operation, but this application is more sensitive where there is a issue with the weight, issue with the complexity. So you can say the like satellite application, space application, where weight is the most important. Suppose you increase the 1 milligram of the weight, then it will create the more issue. Then we can say, yeah, yes, we have to do the sensory operation. But in the case of the electric vehicle, suppose you increase the maybe the 1 kilogram weight, yeah, maybe the 1 milligram weight, that is not issue. But where sensitive application is there, suppose medical application, so there we have to compromise with the weight, correct? So we cannot increase the weight like 1 milligram even, correct? So specific application we can always operate the like sensorless operation, but somewhere maybe there is a not issue in the weight and size, then we can go with the sensor based operation. Yes. Now any confusion apart from the ASIS? If you have still any confusion, then please ask me. For the other student,
No, sir.
other
Let's go.
student, yes, yes. Any other query? Any other confusion? Only ASIS is active, and other all are sleeping. Yeah, what?
No, sir, no, we are listening.
Yeah, you are listening. Very good, very good. So no confusion, no query.
Everything is asked by Ashish, so no query, sir.
Okay, so you are follow the ASIS. Good,
It's
good.
something like that, sir.
Good. Okay, so this is a mere concept. So whenever we can say the sensorless operation, sensorless means that is only we have to remove the rotor position. Okay, not the voltage and current sensor. Okay, it must be used the voltage and current sensor whenever we can say drive. Okay, but sensorless means we have to remove the encoder. There is a encoder, resolver, anything. There is a dependent to rotor position. Yeah. So how many methods are available for the sensorless control? Okay, so we can say open loop, closed loop, and non-ideal property. So whenever we can say the sensorless control method, so we can classify in the three category. Two category already you know, there is a open loop and the closed loop, correct? On open loop we can say the back EMF base and stator inductance calculation. So suppose you want to control your motor in the open loop mode, okay? Then we can say we can sense the back EMF signal, okay? And otherwise we can say the stator inductance calculation. But in the case of the closed loop, suppose you want to control the motor in the closed loop, precise operation, correct? Then we can say SMO stand on sliding mode observer, okay? There is one algorithm, there is a sliding mode observer. Second one, there is a MRAS, model reference adaptive system. There is a model reference adaptive system. And third one, there is a extended Kalman filter. Okay. So no need to worry about this algorithm. This is for your just information. Okay. If you want to do research on the sensorless control algorithm, then you have to read this all the algorithm. There is a SMO, MRAS, and extended Kalman filter. So based on this literature, then you can propose your control algorithm, correct? But as of now, for the syllabus, you can just remember the name of the algorithm. So there is a, for the closed loop, there is a sliding mode observer, model reference adaptive system, and extended Kalman filter. So many modes are there, but here I written only the selective control algorithm. Third category, there is a non-ideal property. Okay, non-ideal property means there is a high frequency signal injection method. So we have to inject the signal, high frequency signal injection, and then we can sense the rotor position. And low frequency signal injection method. Okay, suppose your PWM frequency is maybe the 10 kilohertz. That is your PWM frequency, correct? So maybe we can add high frequency, that is maybe the 20 kilohertz, maybe the 50 kilohertz. By additional this frequency, we can sense the rotor position. Okay, so there are the many methods are there how we can sense the rotor position. Many methods are there. Okay, I already proposed the two method, and both method already published in the IEEE. Okay, and that both paper are available in the IEEE Explore. Okay, so many methods are there to sense the rotor position. Okay. Yes, so disadvantage I am not repeat again. Okay, already cover in the previous slide. So reduce the reliability, increase the weight, increase the design complexity, and increase the cost and size. So detailed discussion we already covered in the previous slide. Yes, why sensorless operation? This already I told you. Okay. Yes. So suppose there is a model based method. Suppose you refer the model based method. So we can say we have a three type of method. There is a first one is a model based, second is an indirect position sensing method, and third one there is a silency based method. Okay, so this classification, this one there is a control method, correct? Open loop, closed loop, and there is a non-ideal property base. This one there is a method. Okay, so we can say the control technique also. Otherwise, we can say the control technique. Otherwise, we can say the model base. Correct. So model based method, there is a first one. Second one, there is an indirect position sensing method, and third one there is a silency base. Correct. So model based, in this method use the fundamental model of the PMSM. So we have to use the fundamental model. There is a mathematical model to sense the rotor position. Example, stator phase voltage, current, and inductance of the PMSM drive. So we can sense the current and voltage, and then based on the current and voltage, we can calculate the inductance of the PMSM. And once you have an inductance, then we can say now we can easily calculate the theta. Correct? That is a model base. So we can first develop the mathematical model of the PMSM, and then we have to use the stator voltage sensor and current sensor. Indirect position sensing method. In this method, the rotor position is estimated indirectly from the sense the position dependent quantity. So we have to sense the some quantity, and that quantity it is depend on the rotor position. Okay, and what is the name of that quantity? Back EMF component, because EMF that is directly proportional on the theta, correct? So back EMF component, and third harmonics back EMF, correct? So ultimately we have to estimate, we have to sense the back EMF, correct? And back EMF is nothing but your voltage. So by sensing the voltage, we can easily find out the back EMF component. And once we have a back EMF component, then you can easily calculate the position, correct? Third one, there is a silency base, okay? And silency, whenever we can say silency, that is your indirect method, and that is nothing but your that method, that non-ideal property method. Indirect, that is a non-ideal property method. So in this method, the rotor position information is extracted from the position dependent machine silencing, and high frequency excitation is usually required. Okay, so there is an example high frequency injection method. Okay, so these are the three major techniques to sense the rotor position based on the some parameter. Okay, yes, so this block diagram is most important for the exam related. So yes, so you have to write the few theory. So there is a pros and cons, and then simple block diagram for the speed control. Okay, so this figure one, there is a block diagram of the rotor position and speed estimation of the PMSM drive. So starting with the auto transformer, yes, why auto transformer? Because we have to regulate the supply. So suppose this is your three-phase supply. So we have to control this supply voltage, correct? So we can control by the auto transformer. This is a rectifier because we have to convert AC into DC, because we have to operate our motor by three-phase inverter, correct? And inverter output, input of inverter, there is a DC. So this is a capacitor. This capacitor is nothing but DC link capacitor, correct? And this is a voltage and current sensor. So you can see this is a VA, VB, VC, as well as the current sensor. This is a IA, IB. Okay. And suppose that the system is balanced, then we can say IA plus IB plus IC is equal to 0. Okay. So two sensors, two current sensor is sufficient to measure the current of the three phase. And finally, there is a PMSM. But here you can see the absent of the position sensor. Position sensor is not there, correct? So how we can operate the motor without the position? Because PMSM BLDC is not possible to operate without the rotor position, correct? So how we can calculate the position? How we can find out the rotor position? Yes, we have a voltage and current sensor. Based on this voltage and current, suppose the balance system, so we can say minus I and IB, that is a third phase. And then there is a Park and Clark transformation that we already discussed in the first semester. We have to transform the Park 3-phase quantity into 2-phase quantity, alpha beta, DQ conversion, and again the ABC quantity, correct? And why we are doing this thing? So now again I am not repeating, okay, because we have to reduce the complexity and we have to give the power, we have to give the signal to our control algorithm, correct, and digital logic signal. So yes, we have a DQ and DQ voltage quantity as well as the DQ current quantity, correct? So once we have a voltage and current quantity in the D and Q axis, so we can say D and Q axis nothing but DC quantity. Then this DC quantity signal we can give our control algorithm, our controller, correct? And every controller is working for the DC, not AC. Okay, so that's why we can
Yes, sir.
say
Sir,
yes.
here we can use only two voltage sensor like two current sensor. Why three voltage is required, sir? For balanced voltage is there, then we can use two also.
Yeah, you can. Yes, we can remove the only two voltage sensor is also possible. But in generally, what happen in the practical case, system is not balanced. In the theory, we can assume there is a balance condition, but in the practical case, it is not a balance condition.
Yes, sir, but
So
current
that's
always
why.
balanced, sir.
Huh?
Current always balanced or not, sir? Current.
No, current is also not balanced. So maybe you have to take the 3 voltage sensor, otherwise the 3 current sensor. Any one sensor is required, that is the 3-phase. Maybe the voltage, maybe you can take the 3 voltage sensor, otherwise maybe you can take the 3 current sensor. Suppose you are taking the 3 current sensor, then you can take the 2 voltage sensor. But in the practical case, our system is not balanced. But for the theory case, we are considering our system is balanced. But in the reality case, it is not always your system is balanced.
Yes, sir, and that inverter should be PWM inverter, no, sir?
Yes, this PWM inverter, yes.
Yes, sir, and which modulation we use there, sir? Space vector or sinusoidal pulse width modulation?
So that is a depend on your control algorithm. So I implemented in the PhD. There is one is the sinusoidal PWM and one is a random PWM. So one is a sinusoidal PWM, SPWM. There is a sinusoidal and one is a random PWM. So R stand on the random.
Random means what, sir? What do you mean?
Random means that is your PWM frequency is not fixed. So your PWM is on time and off time is not fixed.
And
So maybe
any
this is
difference
your
you
PWM
get,
signal.
any difference you get when you change sinusoidal PWM to space vector PWM?
Yes. So that directly affect on the harmonics and THD. That's why people use the different PWM technique to operate the inverter, because that inverter that is directly depend on the your harmonics. If you have a if your system have a more harmonics, so it will create the ripple, that current ripple, and once you have a current ripple, then it will create the torque ripple. And once we have a torque ripple, then ultimately it is a reduce the efficiency of system. That's why people use the different modulation technique to operate the inverter.
Yes, sir, but how to know which to use in what condition?
So that first thing is the depend on the application, where we have to use the PWM, where we have to use the this PMSM drive, a BLC motor drive, correct? And another thing is suppose you use the space vector modulation technique, yeah, sinusoidal modulation technique, correct? So that is a directly depend on the load, which type of load is there. So based on the few factor, we can easily identify the which type of modulation technique we have to use for our system. So there are the few common factors are there. One is the your motor load, where we can use your motor. Second thing is your power rating. Suppose you want to, suppose your motor rating is a 10 kilowatt, correct? And your inverter is also maybe the, because you have to consider the losses, plus or minus 10 to 15% losses, correct? So suppose your motor is a 10 kilowatt, then you have to take care about the inverter. There is maybe the 12 kilowatt, yeah, maybe the 11 kilowatt, because maybe we have to consider the 10 to 15% of the losses, correct? So depend on the switching operation, we can take the modulation technique. Okay, and
Sir,
third one,
but
that is
ripple that harmonics, we have to compulsorily use a filter after that inverter to remove the harmonics, no sir?
yeah. So suppose you will use the filter, correct? Then you will add the additional component. It will it will it will increase your system complexity. It will increase your size of the your component, your size of your system, not component, size of your system. So that's why people are not focusing on the filter part. That's why people focusing on the PWM technique. Got it?
Sir, but that how to choose main question is that, sir. For example, I don't know which sort of technique give more harmonics, which gives less.
You that's why na, that's why I'm saying. So there are the few factors are there, common factors are there. One, that one is a load, that is a common factor. Which type of load is connected with your system, otherwise which type of load that is connected to your inverter part, correct? Second factor, that is your size of the system, correct? Third thing, that is your power rating. Suppose you use the IGBT, MOSFET, or GTO, which type of semiconductor switch you are using. Fourth one, that is a frequency. Maybe you are operating 10 kilohertz, 20 kilohertz, 1 kilohertz. That is your operating frequency. So once you read that fundamental of the PWM technique, so there are the you read that MH Rashid, in which book you refer in the first semester. That is, I think already you studied that subject, correct? Power electronics in the first semester. Yeah, no.
Space vector not read in detail, sir. Space vector I read once, and I think
Not
it,
not not only space vector, but the fundamental of the PWM. So how we can generate the PWM and then advanced level of PWM. That is maybe the space vector, yeah, maybe the any advanced level the modulation technique that you cover in the first semester, yeah, not.
not taught, sir.
Yes,
I
yeah,
think
no, in the first semester, in the in the
not
MSc, not the BTech.
not taught, sir. Not studied in
No,
first semester in PWM.
no. What I can do? Yeah, because in the first semester we have that power electronics subject, correct? So uh, I don't know. So why faculty is not covered that part, because that part is important for the PWM generation. Because whenever we can say drive, so PWM is most important, and normally we cover that part in the power electronics subject. Okay. So, what I can do for you, I will share you one research paper. In that research paper, actually, I refer in my PhD. So, how we can select the PWM technique, because I used that random PWM technique. I told you I used the random PWM technique. See this one, random PWM. So, I implemented random PWM as well as the sinusoidal PWM. Correct. So, both technique I implemented for the PMSM drive. And then I compare this both technique with the for the acoustic noise and vibration. So I will share that paper with you, so you will get the idea how we can select the various modulation technique. Is it okay?
Okay, sir. Okay.
Yeah. Uh, and finally, there is a FPGA estimate algorithm. So maybe FPGA you can use the typhoon hill, yeah, any type of control algorithm. And finally, we can get the speed. Sorry, theta speed and sine theta cos theta is simple. Once you have a theta, then we can easily calculate the speed and the sine cosine factor. Yes, this is a detailed diagram. So reference speed, PI controller, there is a speed controller. Okay. Then we can say inner control loop and outer control loop. Just yeah. So we can say inner current, inner loop and outer loop. So inner loop, there is your current control loop. Inner loop, that is your current, and outer loop, that is your speed loop. Okay. Yeah. Then conversion, there is a part to clock and clock to park, and finally this is a sinusoidal PWM. So maybe you can use any type of PWM, and then inverter and PMSM drive. So here you also missing that sensor part. Okay, we have to sense the current and voltage. Okay, and based on the current and voltage, we can calculate the theta. Correct. So this rotor position estimation block. Okay, and how we can estimate that, I will explain the mathematical step by step process. Okay. So once we have a theta, then we can convert sine and cosine function. Why sine and cosine? Because whenever we convert into dq to alpha beta and alpha beta to dq, it is required the sine and cosine factor. Correct? We already know cos theta, sine theta in the dq reference frame. Correct? So for that we need to convert. We need to find out the sine theta and cosine theta. Correct? And then we can find out the ABC to alpha beta to DQ. Okay. Yes. So these are the mathematical step. Okay. How we can estimate. Yes, we have a voltage sensor and current sensor. So we have a 3 voltage sensor and we have a 2 current sensor. Suppose your system is balanced. Okay. And here we are assuming the system is balanced. Okay. Yeah. So expressing the 3 stator voltage and current in the term of the stationary reference frame. Okay. So here I consider the stationary reference frame. So there are the 2 reference frame. One is a rotational reference frame and another one is a stationary reference frame. So suppose we are considering the rotational reference frame, then it is a system is a little bit complex. But stationary reference frame, so little bit is easy, correct? So here is a stationary reference frame. So VQ and S indicate the stationary is equal to VAS. So I can say on the Q voltage that is equal to VAS. Okay. And S, that is your stator voltage. Okay. Superscript S, that is your stationary, and subscript, that is your stator part. So similar we can write for the D axis voltage, there is a VCS minus VBS divided by root 3 because 3-phase system. So we can say for the Q axis voltage, that is a VAS. Then we can say for the D axis, so we can say this is a Q and this is a D. Correct? And both are the 90 degree. Okay, generally that is a 90 degree. And we have a 3-phase system, correct? So we can say VABC. And S indicate the stator. We can say VABC, this is a rotor. But in the case of the PMSM, we can say on the rotor side there is a no winding, correct? So we can say simple permanent magnet. Okay, for the stator we can say ABC. So we can say for the D axis there is a VCS minus VBS divided by root 3. Why root 3? Because of the 3-phase system. And we know there is a derivation, correct? Why root 3? How we can get the root 3, correct? Similar, we can write for the current IQ is equal to IAS. Once the IQ, then we can say ID, that is ICS minus IBS divided by root 3. Okay, so that is equation number 1, 2, 3, and 4. Correct? Yes. Now we can say the D axis voltage. Okay, there is a excitation voltage. Okay, so there is a RD. So we can say yes. Suppose per phase equivalent circuit. So we can say L, R, and back EMF, EB. Correct. So this is the equivalent circuit of the per phase. Correct. So we can write VD voltage. Okay. Suppose you want to write the VD voltage. There is a voltage D axis voltage for the equivalent circuit. So we can say RD plus P. P stand on the D by dt. P stand on d by dt, there is a derivative part, P. LD, there is a dx is inductor, IDE, there is a current flowing through this circuit, minus omega E LD into IQE, correct? For the D axis. For the Q axis, there is a RQ plus P into LQ, IQE plus omega E LD ID plus omega E into pi x. Okay. So these are the important equation for the voltage. Okay, equation number 5 and 6. And this is a per phase equation.
Sir. So that first two equation I cannot understand, sir.
Equation number 1.
That yes, sir. That is ABC to DQ transformation without having that cos theta. How you transform in that way, sir?
Without
That theta value we have that part transformation matrix cos theta minus 120. Without having that matrix, how you directly write in terms of DQ, sir?
without the theta value, correct? You are saying without the theta value.
Yes, sir. Yes, sir. The theta matrix is there. Cos theta minus 120, cos theta plus 120, sin theta. That matrix is there. No large matrix. That will take your ABC to DQ. But you have directly written this VQ equals to VAS. How, sir?
So there is a simple concept. That's why I remove that equation, because that we already covered in the first semester, correct? So ABC to DQ conversion matrix, that 3 by 3 matrix, correct? Cos
Yes, sir.
theta minus 180 degree and cos theta plus 120 degree. So this already we cover in the first semester, correct? So that's why I remove that part. And your question is without theta, how we can write this conversion, correct?
Yes, sir.
So
In the previous block, we have taken that theta also.
yes,
Here theta and that from
yes.
position speed elimination estimation. There you have taken theta also into that block. That
So theta,
DQ to
ultimately our
alpha beta
target
block.
is we have to estimate this theta. We have to
Yes, sir.
estimate
Yes,
this
sir.
theta, correct? And how we can estimate this theta? By three phase voltage, there is a VAB, VBC, VA, VB, and a VC. And how we can get this VA, VB, VC? By voltage sensor. We have this voltage sensor, correct? We have a 3 voltage sensors, correct? Once we have a voltage sensor, then we can convert a VABC to DQ transformation, correct? Okay.
Yes, sir.
And this transformation, then we can get that VQ and VD quantity, correct? And this is in stationary frame, not the rotational frame. That's why I returned that there is a superscript, that is a S, VQS. And this superscript S indicate the stationary frame. So we have a two frame. There is a stationary frame as well as the rotational frame. Suppose you are going the rotational frame, so little bit is complex because system is rotating, correct? In the stationary frame, that is a little bit easy, correct? Once we have conversion, there is a VD and VQ. Then we can calculate the that part, there is a theta. And once we have theta, then again we can give in the conversion part. Then we require there is a theta value for the conversion part. Now got it?
Sir, I think main theme of this approach is to derive theta from voltage and current.
Yes.
From voltages, three-phase voltages, without using sensor.
Yes.
So we have to understand how that transformation is happening. That first two equation is important.
Yeah, that's why I'm saying now. So here is a voltage, correct? This one is a VA, correct? And we have only two quantity, there is a DQ axis. So this is a D and Q, correct? So we can say D and Q both are the 90 degree, correct? So in generally, D and Q both are the 90 degree, correct? So for the initial condition, I assume theta there is a 90 degree, correct? There is a VD and VQ, there is an angle between the D axis and Q axis, there is a voltage with current, both are the 90 degree, correct? because as a standard, suppose your system is stationary, it is not rotating, so that angle between your voltage and current, that is your 90 degree. Got it?
Yes, sir. I think the first one is your VAS, means your PQ is your phase voltage, and second your VD is VC minus VB, that is your line voltage divided by root 3. So that is also measuring phase voltage. So how that Q and D
So
voltage
which one is
becomes
the
your
line
phase
voltage?
voltage?
So which one is line voltage you are saying?
VCS minus VBS, that is VCB
Uh-huh.
measuring.
Uh-huh.
So VD is becoming your line voltage and VQ is becoming your phase voltage. How that is happening, sir?
Can you just repeat?
Yes, so you can see that equation.
Mm-hmm.
V,
Equation of 1 and
VAS
2,
means
correct?
your stator side phase voltage, right?
Mm-hmm.
And VCS minus VBS is your stator side line voltage.
Mm-hmm.
Now, how your Q axis voltage becomes your uh, phase voltage? That is my question.
Q voltage is a phase voltage.
Yes, sir. Yes, sir.
Just 1 minute. Q voltage is a phase voltage. So this is a star connection. So there is a three-phase star connection system. So line voltage equal to root 3 times of the phase voltage. Line voltage equal to root 3 times of phase voltage. So this is your line voltage and this is your phase voltage. Mm, I don't know this thing. So you are saying this is a line voltage and this is your phase voltage. So how that is possible? But in the DQ axis, I don't know.
Because
I
of
have to
that
check this
DQ
thing.
values are DC values, DQ values are DC values, but VAS, VBS, VCS are RMS values.
Yeah, there is a RMS
How
value.
that is?
But there is a conversion is there, but I don't remember this thing now. Uh, yeah, I don't know currently. Uh, I have to check this thing. I will check this thing. That VD and
Okay, sir. Okay.
VQ, that is your line. There is a DQ axis voltage and there is a phase voltage and line voltage. It is based on star connection system. There is a line voltage equal to root 3 times of the phase voltage. No, currently I don't know. Yes, I have to check that thing. Yes, so I will check that thing and then let you know. Okay. Yeah. So yes. Any other query apart from
Yes,
the
sir. That
equation of 1 and 2?
five, six equations are clear, but we have seen this. One, two, three, four. Major equations are one, two, three, four.
Yeah. So 1 2 I will check that thing. So there is a RMS voltage and D axis and Q axis voltage. So because only equation of 1 and 2 is major issue, because second, third and fourth one there is again current. It is the same like the voltage. So once that we know the voltage equation, then yes, we can say it is a current equation. So I will check this thing. I will check this thing. That VQ, there is a VS, and VD, there is a VCS minus VBS divided by root 3. I will check that thing. Okay. So for the equation of 5 and 6, any confusion? Per phase equation. Yes, Asis. And for equation of 5 and 6, any confusion?
So 5, 6, no confusion, sir. 5, 6.
Okay.
We have
So
seen this
first and
several
second
times.
equation, I will check that thing and get back to you. Okay. Yeah. So transforming the stationary frame to rotatory frame. Yes, so ID we can say ID S cos theta E plus ID IQ sin theta E. So now we can say it is a rotational frame, correct? So now we can say it is a rotate from stationary to the rotation part, correct? So we can say there is an angle cos theta and sin theta, correct? And for the stationary part, we assume that is theta is 90 degree, but here is a rotating frame. That's why here written that is a theta e, because now rotation is rotating, correct? So we don't know what is the value of the theta. So we can write cos theta e and sin theta e, correct? That is the equation number 7. Any confusion in equation number 7? Any confusion? So there is a d axis and q axis, and that d and q axis, that is a depend on you. Maybe the on x axis you consider the d, and on the y axis maybe you consider the q, correct? So as per the your conventional, you can write this equation, correct? But theta e, that is a not a constant value because it is a rotatory, so we can write it as a theta e. Okay. Yes. Okay. Similar light we can write for the d axis. Sorry, the that one equation number 7, that is a d axis. So this is a q axis. There is a minus id sin theta e and minus plus iq cos theta e. That is equation number 8. Similarly, we can write the vd and vq. Okay, that is equation number 9 and 10. Okay, and finally for the omega e. Okay, and one more thing, this equation is not important for the exam. Okay, important for this exam, there is a figure number 1 and figure number 2, but still this equation is important for your research work and for your understanding. Okay, that's why I'm explaining this equation, and whatever you have confusion, please let me know. So I will again refer the book and then let you know, so from where we can get this equation, correct? So till now I got only one confusion, there is a equation number 1 and 2. Okay, and finally there is omega e. Okay, this omega e that we can calculate the based on the flux of the motor and the voltage equation. There is a per phase voltage equation. Okay, so this is a very difficult equation, so I don't have a proof for this derivation. Okay, so how we can derive this equation? There is omega e. Okay, so putting the value of IDE and IQE from equation 7 and 8. Okay, so from equation 7 and 8 we can find out, we can put in the value of ID and IQ into equation number 5 and 1. Okay, so what is the equation number 5? So this one 5, and equation number 1 there is a VQ with equation number 10 and 11. So we can get theta. Theta is what? Tan inverse x by y. So from this equation we can find out the theta. Theta is what? That is a tan inverse x by y. Correct? And what is the value of x? There is a minus Vd Id plus Ld Pdi by omega E Ld Lq minus Ld. Correct? And similar for the y. Okay, so by using this thing we can calculate the theta. Yes, so this is the equation. So still now only one confusion, that is for this sensorless operation, there is equation of 1 and 2. Correct? Correct, Ashish? Any more confusion for this equation? Yes, Ashish. Any more confusion for this equation? No? Ashish, are you there? Okay. Yeah. Madhusudan, are you there? Yes. Okay. So last 5 minutes, I will take only 5 minutes. So this is the simulation result of the sensorless PMSM drive. So this is for you just information. So you can see this is a theta response. Okay. So this is a speed. You can see dynamic operation. So increasing So this is increasing and then is a constant for the some time and again decreasing and the increasing. So you can see the reference and actual speed, that is a error is a very very small error, otherwise negligible error. Correct? So same, that is a your D and Q axis. So D axis, there is a direct axis, there is a amplitude, and the Q axis amplitude, and figure B, that is your voltage, phase voltage. Okay, there is a sinusoidal, and this current, there is a IVA, IB, and IC. There is a current. Okay. Yes. Interesting result. There is a theta. So you can see the rotor position estimated. There is a red one and blue one. There is a rotor position by the sensor. So you can see error is a very less error. Okay. And for the speed, so we have to compare the speed. There is actual speed. There is a sensorless actual speed, sensor base actual speed, and our reference speed. So you can see that error is around like 10 rpm. So sensorless error, there is only 10 rpm that error. So we can also reduce this error by the proper tuning of the PI controller. Okay. Yeah, so this is an angle, there is a theta. Okay. So sine angle and cosine angle for the both the sensorless and sensor. Yes. So finally, key point. So there is an introduction of the PMSM, drive, difference between the BLEC and PMSM, and then working principle of the PMSM drive, and then speed control of the sensor and sensorless PMSM and sensorless operation of the PMSM drive, and finally the result discussion on the simulation. Okay, so most important for the exam related, for the one maybe the 5 to 6 marks, there is a introduction of the PMSM drive. So maybe the just 2 to 3 lines. Okay, and then this block diagram, there is a sensorless operation block diagram. Okay, there is a this block diagram. So block diagram of position and speed estimation of the PMSM drive. Maybe you can draw this one, yeah, otherwise this one. Okay, so there is a vector control of the PMSM for the estimate the rotor position. Okay, and then you have to just explain this block diagram. Okay. Yes, mathematical is not important, but still you should know about this mathematical equation. So I got one query from the ASIS, that is a VQ and VD voltage. Okay, so I will find out. I will check again in the book, and then get back to you. Okay. Yes. Any more confusion? Any more query? And one more query. There is a IM. Yes, this IM. So IM stand on the internal mounted motor. Yeah, there is a induction motor, correct? So I will check this thing also. Yes. Any more confusion? Any more query from the today's class? Yes, student. Any more query? Any more confusion? Yeah. So this is the last class. If you still any confusion, any doubts, and regarding any exam, then please let me know. Yes. Yes, Ashish, any more confusion, any more query? So from the today's class, I got the two
No,
query
sir.
from
No,
you.
sir.
The induction motor, that is IM, and second one, that is your sensorless equation, that is a VD and VQ. Okay, so I will check in the book and then again get back to you. Is it okay?
Okay, sir.
Yeah. Okay. So thank you so much. If you have any query related to exam, then please let me know. Okay. Then thank you so much. So we can close today's class. Bye bye. Good night. Have a nice day.
Good night, sir.
Good night. Good night.